Okay, and we've tested many Chicago figs. There's a whole industry built around it, and we know that the average Chicago fig has 10 grams of sugar in it. You want more sugar because they're sweeter, they're nicer, plumper, and so on and so forth. So that's how much sugar on average that they have, each fig. So let's say that we also know that the standard deviation, the variability of sugar in these figs, is 1 gram. Okay, 1 gram is the standard deviation for each fig. Okay, and this is something that we know about all the Chicago figs. Notice I use Greek letters, meaning that we're working with parameters, which means that this is a population mean and this is a population standard deviation. Right? Okay, so let's say that I go in my yard and I sample, I'm going to sample 36 figs, right? That's how many happen to be ripe right now. I picked 36 figs, but let's say I have a nice grove of fig trees. I have 100 fig trees, and I go randomly around and pick 36 figs. And it turns out that the mean, right, n is equal to 36, the mean level of sugar in each fig is equal to, let's say 9 grams. Let's say 11 grams. So now let's say I want to demonstrate that, gee, I think my figs are sweeter than Chicago figs. Right? I think that I have the edge on that. The average Tony fig is sweeter than the average Chicago fig, right? Well, I'm going to start with an assumption here. I'm going to look at this 2 ways, right? One way is that if I took a sample of size 36 from Chicago fig trees, what's the likelihood that I would get an average like 11 or 9 in that sample of 36? Well, I'm fortunate because I know the true mean and the true standard deviation for the entire population. So I actually can predict that the average sample that the average for each sample that I took would be 10 grams of sugar, right? Would be 10. And the standard deviation would be 1 gram. In other words, if we just look at the empirical formula for right now, in other words, that 95% of the samples that I would take would have a mean between 2 standard deviations below, in other words, 8, and 2 standard deviations above, in other words, 12. Okay. Well, since it's sigma, I know what sigma is. I can really be a little bit more precise, right? I can really say 1.96 standard deviations below 10 and 1.96 standard deviations above 10. So if I took samples of size 10, I know what the likelihood that I would get a 36 figs that I take sample. I know that there's less than 5% chance that I would get an average more than 12 and less than 9. Okay, just sampling over and over and over again. Okay, well that's interesting, right? Let me look at it from another perspective, though. Let's say that we know that the mean sugar level in each fig, Chicago fig, is 10 grams, and I want to compare it to my figs. Well, I don't know what mu is for my figs. I'd have to sample every fig, right, and send it to the lab and have them tested. I don't want to do that. I want to eat some of them, right? So I'm not gonna analyze every fig. Let's say I sample 36 figs. Okay. So now, if I sample 36 figs, what's my confidence interval for the true mean, for what the true mean is for the level of sugar in my figs? Well, the way I would figure that out is I would say X bar plus or minus. Well, this is a pretty big sample, right? I could argue that's a big enough sample that I'm going to use the z-score. I'm not going to worry about using the t-test. I'm going to use the z-score. The other argument I could make is I could make the argument that, even though my figs might have more or less sugar than the Chicago figs, maybe they'll have the same standard deviation. So maybe I could argue I know sigma, or on the other hand, maybe I can argue that's a big enough sample that I don't have to worry about the t-score. So I could say X bar plus or minus 1.96. I'll use the z-score for alpha is equal to 0.05, 2.5% on one end, 2.5% on the other, times the standard error. Okay, so what's the standard error going to be equal to? Standard error is going to be equal to sigma, right? Which is, there's two ways I could get sigma here. One is by getting standard deviation from my sample, which would mean maybe I got to use a t-test if my sample size wasn't big. Or I could assume that I know sigma is 1 gram. So I'm going to assume that I know it. So I'm going to say that sigma is equal to 1, the standard deviation, divided by the square root of the sample size. 1 divided by the square root of the sample size, which is 36. That's equal to 1/6. Can anybody tell me what fraction 1/6 is? 6 and 1 is 0.1, whoops, 0.1, 4, that's 6, 0.167. Yeah, it's half of a third, 0.167. Okay, so the standard error is 0.167. So my 95% confidence interval for the true mean of my figs is going to be 11 plus or minus 1.96 times 0.167, 1/6. So I'm going to multiply this out. So it's going to be 11 plus or minus, right? And that's 1/6. That's going to be 2/6 now. So it's going to be plus or minus 0.33, right? So my 95% confidence interval is going to be 10.67 to 11.33. Okay, that's my 95% confidence interval. What does that tell us? That tells us we're 95% certain that the true population mean for my figs is between 10.67 and 11.33, right? So what are the odds that they're lower than 0.67, 10.67, right? Or higher than 11.33? Well, it's only 5% chance of that happening, right? Or really less than a 5% chance of that happening. So if I told you that Chicago figs are known to have an average sugar level of 10 grams, we know with 95% certainty that my figs have more sugar in them than the Chicago figs, right? What if I told you that Chicago figs had, the mean Chicago fig had an average sugar level of 10.8? Would I still be able to make that statement? No, I wouldn't. Why wouldn't I be able to make that statement? Because it's entirely possible that my figs might not have that level. My true mean might be less than 10.8. At least I don't have enough evidence to say that it's 95% chance that it's different, right? So we're using the confidence interval here to try and determine whether we have enough evidence to say that our sample demonstrates that the true mean of the population that we're examining is different than a certain number. In other words, if it's outside of our 95% confidence interval, the value we're comparing it to is outside of our 95% confidence interval, we're 95% sure that our mean is different than the mean of the thing that we're comparing it to, this mean. Right? So that's interesting. That seems like a useful thing. Most of the time we don't know. We don't know either mean, right? But on occasion we do know a set value that we want to compare it to. This seems pretty useful, right? So things get complicated fast though. Let's say we don't know either mean. Let's say that we're dealing with a mean for one sample and a mean for a second sample. Well, then we have two confidence intervals, right? Confidence interval for this mean and another confidence interval for this mean. Well, you know, if the confidence interval for this mean is 10 to 12, and the confidence interval for this mean is 14 to 20, you know, it looks like there's pretty good evidence here that the true means from the populations that these are based on are likely to be different also, right? But if they overlap, right, well, all bets are off now, right? In other words, we're not 95% sure that they're really different. Okay, well, this is kind of an awkward way to do this, right? There's a lot of things that can go wrong here. Among the many things that could go wrong here is that the variability of one group could be different than the The other group, there's a million things that we could have issues with here. So we're not going to do it exactly this way. We're going to do these kind of comparisons a little bit differently. We're going to do something called a t-test. Before we get into that t-test, right, before we get involved in that, let's make sure that we really understand how to do confidence intervals. Okay, so, and when we use the z-value and when we use the t-value. Okay, so I don't know what mu is, and let's say I don't know what mu is, but I know that for this population, that sigma is equal to 10. I know the standard deviation of this this population is 10. Does that come up very often? No, but it comes up occasionally where someone may have done a study where we believe that study was so large that we have a pretty good idea of what the population standard deviation is for this kind of variable might be. So let's say that we're assuming that we know what that is. Well, since we know what that is, we can calculate with some certainty what the standard error is based on the sample size that we take, sigma over the square root of the sample size. Okay, so let's say that I take a sample, x bar is equal to 100. My sample size happens to be 25. Right? Actually, I'm going to change that. I'm going to make my sample size 64. I'm going to be more extreme. I'm making my sample size 100. Okay, so I know sigma, I know my sample size, I know the mean that I got for my sample size 100. So my standard error is going to be equal to 10 divided by the square root of 100, which is 10. It's going to be equal to 1. Right? So that's my standard error. Right? So my 95% confidence interval is going to be x bar, which happened to be 100, plus or minus. Well, now I got to decide, can I use the z-score or should I be using the t-value for the value I want for the 95% confidence interval? Well, let's see, I got two reasons here why I can use the t-score. One reason is I know what sigma is. And since I know what sigma is, I can calculate my standard error with a lot of confidence, right? On the other hand, I also have a very large sample size. Either one of them, we know a sample size of 100 is going to give us a t-value of like 1.97 and 1.98. It's going to be so close to the value for z that we may not feel uncomfortable just using 1.96. And we could argue that since it's such a large sample size, we can actually even use the standard deviation of our sample to determine what sigma is, to estimate what sigma is. But for argument's sake, right now, we know sigma, so we can use our z-score. It's going to be 1.96 times our standard error, which is equal to 1. So our 95% confidence interval is 100 plus or minus, forgive me, I'm going to use 2 here, 2, right? It's going to be 98 to 102, right? If you want to be more accurate, it's really going to be 98.02 to 102, 101.92, I think, right? Yeah, I think I'm right. Okay, 101.92. It's going to be adding 1.96 times this. I'm going to be adding and subtracting 1.96 from each side here. 101.9. Oh, you're right, and it's 98.04. Yes. Okay. So that's our 95% confidence interval for the true mean for the population that the sample is derived from. Okay, let's do this again. Exactly the same numbers, except this time, I'm going to take a sample of size 25. Let's say x bar is equal to 100. The sample size is equal to 25. And we don't know what mu is, and we don't know what sigma is. We don't know either one of them. However, we know that the standard deviation for this sample, right? The standard deviation for this sample is 10, right? It actually approximates the standard deviation of the population, right? So it's going to approximate the standard deviation sigma for the entire population. So we're going to use standard deviation is equal to 10 to represent sigma, because we don't know what it is. That's our only way to interpret this, right? Because we have no other evidence what it's going to be. So let's calculate our 95% confidence interval now. It's still going to be x bar plus or minus. And now we got a little bit of a problem here. Should I use 1.96 here? Well, I can't justify it anymore, can I? I don't know what sigma is, and my sample size is small, right? So because our sample size is small, I don't have very much confidence that I have a good handle on the standard deviation of the population. So I have to make up for that lack of confidence by creating a wider confidence interval for 95%. And I do that by using the t-value for 0.05 instead of using the z-value for 0.05. So let's get our t-table. Okay, it's in this session we have copies of the t-table. Okay, so let's look this up. So our sample size is 25. How many degrees of freedom does that represent? That represents 24 degrees of freedom. So our 95% confidence, or t-value that we want for 95% confidence for t for alpha over 2. In other words, left tail and right tail each being 2.5%, right, as they show here. Or in other words, overall alphas being 5%. Our overall, our z-table, our t-table tells us that we should be using a t-value of 2.064. So this is going to be equal to 2.064 times our standard error. Now, our standard error now is going to be equal to, instead of sigma, the standard deviation over the square root of 25. In other words, 1 over 5, 10 over 5, right? What's it? And yes, 10 over 5. It's going to be equal to 2. So our 95% confidence interval is going to be 100 plus or minus 4.132. Okay, right? No, 128. 4.128 plus or minus 4.128. So that's going to be equal to 104.128. And on this side, it's going to be equal to 95.872. Is that right? Okay. So that's now our confidence interval, right? It's wider than it was before, right? It's wider than it was before for a couple of reasons. One is that we had to use this t-score, right, instead of the z-value. And the other reason is because our sample size was smaller, our standard error became a larger number. Okay. So that's our 90. We're 95% certain the true population mean for the population that this sample was taken from is between these two values. We're 95% certain of that. Okay. So when am I using the t and when am I using z? I'm using z when we know sigma, population sigma, and I'm using it when we have a large sample size, right? Large enough that we have a good handle on what we think sigma is. In other words, we can use a standard deviation sample to approximate sigma with a high degree of confidence, right? And what would that sample size be? We've been debating this for a while, right? How about if I just said that a sample size 100, we're pretty comfortable with that, right? Sample size of 30 or 40 or 35 or 40, we're less comfortable with. Right? So maybe we'll stick with 100. Right? 35 or 40 is nice because we can start to assume that the central limit theorem gives us a pretty normal distribution of sample means, right? Even if the population mean isn't perfectly normal, but it may not be the best approximation of the confidence interval. So maybe we'll start calling, for our purposes, we'll call a large sample size 100. Okay, so going forward, I'm going to try and stick with that. Okay, so now let's take a look at another way that we might examine this. Okay, so I'm going to get away from the figs and pick something else out. Okay, so let's look at blood pressures. The average diastolic blood pressure is I take a sample of 100 people, certain age, certain weight, certain BMI range, gender, so on and so forth. Some population of people, I take a sample of 100 people, and I say to myself, okay, the mean blood pressure from this sample of 100 people came out to be 80. And the standard deviation for that sample of 100 came out to be 10. Okay, so now I have another population. In this population, we happen to have sampled every person in this population. Everybody was sampled. So I know what mu is for this population. Turns out that mu for this population is equal to 83. Okay? So I want to examine, boy, it looks like my population has a lower blood pressure than this population does. Right? Well, I want to determine whether or not that I can say my population is different than this population with 95% certainty. 95% certainty is kind of another way of saying that you have less than 5% chance of being wrong. Right? If I'm 95% certain, it kind of means that I'm less than 5% chance. I'm agreeing that the chances of my being wrong are 5%. Right? Well, you know, before I took this sample, I didn't know if my population was going to come out 80, 85, 79, 115. I didn't know what I was going to get before I took the sample, right? So before I took the sample, I was not going to be able to predict whether or not my sample average will come out higher or lower than 83 for this other population, right? So you know, I'm gonna create a 95% confidence interval, and I'm going to assume that I didn't start out knowing whether it was going to be more or less than 83. Right? So I'm going to take my 95. I'm going to calculate my 95% confidence interval. So X bar plus or minus big sample, I'm going to use 1.96 times standard error is going to be equal to 10 over the square root of the sample size is 10 is equal to 1, right? So my 95% confidence interval is going to be roughly 80 plus or minus 2. It's going to be 78 and 82, roughly. I'm not going to bother with the decimal points. Okay, so I'm 95% sure my true population mean for where the population I took the sample from is between these two values, right? Well, what is this? The population I'm comparing it to, we know that means it's 83. So I'm 95% sure that that population mean is outside of the confidence interval for my population. So I could say to myself, that means I'm 95% sure. In a sense, I could say I'm 95% sure that my population has a lower blood pressure than that population. But you wait a second. Didn't I say I didn't know it was going to be higher or lower? So if I was doing this from the start, I would probably just be saying to myself, you know, I want to know whether it's different. I don't know in advance whether it's higher or lower. So I'm going to be satisfied with saying that I'm 95% certain that my population has a mean that's different than this other population. Okay. Well, you know, it's 83 versus at the high end 82. Yeah, it's a bit away from our average. I wonder if I actually think what the probability is that we're wrong here. That can I go to 99% confidence and still say that? Can I go to 99.9% confidence and still say that? Let's take a look at this and see if I can't do something interesting with this. Okay, so I'm going to take my distribution of sample means, 100. And what I say standard deviation was equal to 2. Right? Sigma, that's the standard error, right? It's equal to 2. Right? So what's the probability if I took a sample of size 100? What's the probability that I would get? Oh, I'm sorry, this was 80. what's the probability that I would get an outcome as extreme as 83, the value of that other population? Given our sample size, given the result that X bar was equal to 80, and that the standard deviation was equal to 10, right? And that standard error is equal to, I'm sorry, that was equal to 1. Right? Equal to 1, standard error is equal to 1. Given all of that, what's the probability that we would have gotten a mean that was a sample mean, when we took a sample size 100, as extreme as 83? What's the probability? Well, we know that our confidence interval was between 78 and 82. So the probability that we would get that extreme a value is certainly less than 2.5%, right, on the high end. Right? Or a lower probability of getting a sample mean that's greater than 82 and less than 78 together would be 5%, right? Because 95% of the time we get a value in between those. Well, let's see what the probability is that we get that extreme a value. So how much is left in that tail at the end there above 83? What's the likelihood we get that extreme a value? Well, let's see. First thing we need to know what the z-score is for that value. Right? So what's the z value for that value? It's going to be equal to x minus mu over the well, in this case, standard error, because standard error is our standard deviation. So what's it going to be? It's going to be 83 minus 80 over 1 is equal to 3. It would be a z-score of 3. How big an area is left in there? Right, if that z-score is 3. Let's go to the z-table. Okay, z-table, z-score of 3.0. I'm going to look at negative 3.0 because it's easier. Negative 3.0 is 0.0013. That's 0.13%. Okay, so that area, since it's symmetrical, this would be equal to 0.0013. And this would be at this end, if we were negative, if it had come out to be 79, we'd be down here, and the probability of getting that extreme value would also be 0.0013. So what's the probability that if all this is true, that we would get a value that is as extreme as 83, 3 standard deviations above the mean, or 79, 3 standard deviations below the mean? Well, it's going to be 0.0013 at the top end and 0.0013 at the bottom end. And since I wasn't anticipating whether it was going to be more or less, I'm going to add those two together and say that the probability that I would get that extreme of value, that's 3 standard deviations on one side, 3 standard deviations on the other side, is going to be 2 times 0.0013. Or in other words, it's going to be equal to 0.0026. 0.26%. So that value is the probability that we would be wrong if we said that these two means, our guess at this our X bar for this population, which was 80, and we're using that to estimate the mean for that population, we would be wrong that percentage of the time if there's that extreme a difference between these two values. Okay? So that's one way I could look at this. Let's say it's not that big a sample size. Let's say it's a sample size of only 25. Okay, so X bar is equal to 80, N is equal to 25. Sigma, standard deviation, was equal to, I think, 10. And we're interested in knowing, if we can say with some level of certainty that our mean for this population is different from this other mean, which is known to be 83. Okay, well, let's take a look at this. 83. Okay, sample size is 25. Well, now, I can't use that Z distribution anymore, can I? Because the sample size is small. and we don't know what sigma is. So I really can't use that Z table anymore, right? So instead, I have to use the T distribution. Problem with that is that there's no single, you know, at Z table, we have a single table. It's really two tables, but it's really a single table, right? Represents all the values. The T distribution is different changes for every sample size. The T distribution for a large sample size may look like this. For a smaller sample size may look like this. For a really small sample size may look something like that. So we don't have a table for a sample size 25. We only have a table that gives us certain values of T for specific levels of confidence, right? 95%, 99%, so on and so forth. So let's see what I can do with this. Let's see, the mean is 80. The the sample size is 25. Standard deviation is 10. The standard error this time is going to be equal to 10 over the square root of 25, which is 5, which is equal to 2. Okay, so now let's take a look at that value 83 now. It's value 83. Let's see, where's that going to put me? Right, so the T value is equal to, just I'm looking for how many standard deviations apart are these things? How many t-scores apart are they? Sample size is that. Okay, it's got to be equal to 80 plus or minus the t value, which for sample size of 25 was 2.064, right? Times the standard error, which is equal to 2, right? So yeah, that's one way to look at it. But wait a second, let me look at this another way. How many t-scores apart are those two values? Here's 80. Instead of working out a confidence interval, let's look at how far apart these are. Right? So the standard error is that. Okay, so this is 83. So the number of t-scores, the number of standard errors apart that these are, is equal to 83 minus 80 over the standard error, which is the standard error, which is 2. So T is equal to, which is equal to 1.5, 1.5. I got that right? Yeah, T is equal to 1.5. Okay, that's for a sample size of 25. Now, let's take a look at our T table. Okay, so our T table tells us for a sample size of 25, 24 degrees of freedom, how many standard deviations or standard error apart do we have to be? We have to be 2.06 standard errors apart. Are we 2.0? Are we? How many standard errors apart are we? Only 1.5. So we're not far enough apart for us to say with 95% certainty that these are different. What happened here? How come this happened to us? Well, for one thing, the sample size is smaller, right? So they have to be further apart. The other thing is that our standard error now instead of being 1 is equal to 2 now because of that sample size as well. Okay, so if I wanted to check to see if the value is far enough apart, I can actually calculate whether or not I've exceeded the t value that I need to say I'm 95% certain these two means are different. Okay, so let's see. Had we had a sample size of 100, our standard error would have been 1, right? And we would have been 2 standard errors apart, right? We would have been 2 standard errors apart. Actually, it would have been, 2 standard errors apart, right? So 2 standard errors apart, we still would have been a little bit short, wouldn't we? So let's see. So, okay, let's actually do some actual examples at this point. Okay. I'm going to open this one. I don't like that one. We got a better one. Okay, so let's say we have 10 values. And I think I have this in Excel. Where is it? It should be in here. I guess I don't have it. It's not on Blackboard. Okay, I'm gonna have to get creative here. I'm going to type these values in here since I can't find the file right off the bat. 5, 7, 8, 9. Not exactly nice normal distribution, but we're going to use it anyway. 12, 13, 14. Seven, 8, 9, 10, 11. What's that 11? Okay, don't have to be in order. Okay, so let's find the, this is sample size of 9. And sigma is unknown. Oh, sigma is known. For the population is known to be 3. Sample size is 9. Okay, let's find X bar. That's equal to the average of these numbers. The average is 9.9. So the standard error is equal to, and let's see, we know sigma is 3 divided by the square root of the sample size, which is 9. Square root of 9 is 3. So standard error is equal to 1. So if we want to compare this to a known value for another group of 8, mu for this other group is equal to 8. If we want to determine how many standard errors apart that these are, we can just take the difference between the mean and that mean of our sample and the mean of the other population and divide it by the standard error. And that's going to give us the number of standard deviations apart, of standard errors apart that these are. Whoops. That was supposed to be, let me try that again. Minus 8 divided by 1 is equal to 1.88. That's the number of standard errors that these are apart. In order to be 95, what's the probability that we would get that extreme of value between these two? Well, it looks like it's quite a bit under 1.9. It's under 1.96 for sure. But with since we know the standard deviation of population, these need to be 1.96 standard deviations apart for us to say with 95% certainty that they're different. Okay? In fact, we can figure out what the actual probability is. The actual probability is, let's see, inverse, norm, inverse, I think, or norm dist. Norm S dist. Okay. The actual probability of getting this extreme of value is 97. Let's see. Is 97%? Is 3%? Because they're because 1.96. I should put it down this way. Let me do it this way. 1.98 minus 1.96 over 1. Did I get that right? Yeah, nope, hang on a second. D C8. I'm confusing the issue here. I need to draw this. What I'm saying here is, let me try and clarify this a little bit. I'm sure I've lost you by now. I have, I know. Okay. I'm trying to remember what the means are and stuff. Okay. All right. Okay. Let's assume that our mean is, let's assume, I'm going to work it the other way around. Let's assume that we start with a mean of 8 for a known population. Okay? And if I assume that I take a sample from another group of size 9, and there are the numbers I have for it, and I find that the mean is equal to 9.88. That's all. That mean is going to occur right here, 9.88. It's going to occur there. Okay. How far is that from 8? What's the probability of my getting that extreme of value if these two populations have the same mean? Well, the probability of getting that extreme of value is going to be determined by how many standard deviations apart they are. In other words, what the z-value is for 9.88. As it turns out, that the z-value for 9.88 comes out to be 1.88. Right? 1.88. So this area, the probability I'd get that extreme of value, a z-score of 1.88 from the mean, turns out to be about 92%, about 93%. Right? Oh, excuse me. This is going to represent 93% to the right of that value. So what does that leave here? 7%. Right? Well, if I got a value, if it turns out that that value is 7% chance of that being exceeding that value, right? I also have 7% on this end because I didn't start off knowing whether my mean was going to be a mean for the population I was testing by sampling. I didn't start out knowing whether it was going to be higher or lower. So I have to account for the upper end of this and the lower end of this. So there's 14% chance that I could get a value that far away. So if there's 14% chance of these two means being the same, right, then I can't say that I'm 95% sure that they're different, or that I have less than a 5% chance, 5% chance of saying that they're different and not being wrong. Okay? So the z-score tells us whether we have enough evidence to say that these are different. I got to take the z-score, use it to calculate a p-value, but that p-value only represents one side of the distribution of samples. I have to double that to account for the other side of the distributions to get the p-value, the probability I would be wrong if I reject the null hypothesis and say that these two means are different from one another. Let me try that again, so that maybe I can make it a little bit clearer. As I build on this, maybe it'll get a little clearer as we go along. Okay, and let's start actually building a hypothesis test for a single sample t-test, for a single sample test. Okay, let's see. All right, I'm going to start out with, let's see. I don't want to go to those examples yet. Let's see. I'm going to start out saying that I have a population with a known mean that's equal to 200. Okay, and with a standard deviation of, I'm going to say I don't know the standard deviation. Okay, and I take a sample from a second population. Population 1, this is population 2. Take a sample from that second population. X bar is equal to 195, right? Sample size is equal to 100. I'm going to start a little bit smaller. Say sample size is equal to 25. And the standard deviation of my sample happens to be, standard deviation of my sample happens to be, let's say 10. Okay, so I want to predict whether or not I can say with 95% certainty, in other words, 5% chance of being wrong, right? Less than 5% chance of being wrong, that these two populations have different means. Okay, so let's state a hypothesis right now. I'm going to state that my hypothesis is that the mean of my population 2 is equal to the mean of population 1. Okay. What hypothesis is that? That's the null hypothesis. Okay. My alternative hypothesis is that they're different. mu2 is not equal to mu1. Right? Do I know? Am I predicting whether one is bigger than the other? Yeah. No. Okay. Good. So this is a two-tailed hypothesis, two-sided or two-tailed hypothesis, right? This is our alternative hypothesis. Okay, so what are my assumptions here before I take this? What are my assumptions? My assumptions are, for starters, that this sample that I took is random, right? And the population it came from is roughly normal, right? So I've taken a random sample from this population. Every person in this population has an equal likelihood of being selected, right? So now I want to predict whether or not these two values, 200 and 195, are far enough apart for me to say with 95% certainty, in other words, less than 5% chance of being wrong, that they are different. Okay, so let's take a look at this. In order to calculate that, I don't know sigma, right? So I'm going to calculate how many standard deviations apart, how many standard errors apart are they. So I'm going to call that T, not Z, because I don't know, because I don't know a population standard deviation. It's a small sample. So the number of standard errors apart is going to be equal to the difference in the two means, in other words, 200 minus 195, over the standard error. What's the standard error? What's our calculation for the? Well, we're using standard deviation because we don't know what sigma is. 10 over the square root of the sample size is 5 is equal to 2. So how many standard errors apart? What's our t-score? It's equal to 5 over 2 is equal to 2.5, right? So we didn't know in the beginning whether this was going to be 5 above. It could have been 205, in which case our t-score could have been negative 2.5. Right? So if I draw this as a distribution, how far apart are these two means? Well, they're 2.5 standard deviations apart. I didn't know in the start whether they'd be 2.5 standard deviations apart on the top end or the bottom end. So my conclusion is that the probability of me getting that extreme a difference between these two is going to be negative 2.5 standard deviations apart on this side, negative 2.5 standard deviations on this side. So what's the probability of this happening? What is the probability of this happening? Well, you know, I don't have a z table to go to find this area, But what I can go is to go to the t-table, and the t-table will tell me what t-score is needed for this sample size for me to be able to say that there are more than 2.5 standard deviations apart on this side and more than 2 standard deviations apart on this side. Right? So I can find a value of t that if I exceed that value of t, that I can say there's less than 5% chance, that there's less than 2.5% chance at the low end, 2.5% chance at the high end. There's less than 5% chance that this sample came from the same population distribution as this known mean did. That these two populations have the same value, same mean. Okay, so what does that t-value have to be? Whoops, that's my t-table. So for sample of size 25, that t-value, 24 is 2.064. So are they more than 2.064 apart? Oh, where'd they go? They are, right? So since they are, since my value of t that I calculated, right, is equal to 2.5, since that's greater than my critical value of t, the value of t that I have to exceed, in other words, number of standard errors apart that I have to exceed, which was equal to 2.064. Since that t is greater than my critical value of t, I can say that my probability of being wrong, if I reject the null hypothesis and say that they're different, is going to be less than 0.05. And since it's less than 0.05, which is alpha, which is what our tolerable level for error is, since less 0.05, I can reject the null hypothesis and accept the alternative hypothesis. Now, what if I had done this and t came out to be 2.0? Did I exceed the critical value of t, which was 2.064? No, it's smaller than that. So in other words, it would have been inside of this line, which represents 2.5% on either side. So in that case, could I reject my null hypothesis? No, I can't reject my null hypothesis. So I failed to reject my null hypothesis. I don't say I accept my null hypothesis. I don't make any conclusions about it at all. I just say I failed to reject it. Okay. So let's give it another try. Let's do something interesting. I'm going to take my Excel file, which if I can find it again, where'd it go? Did I close it? I did. I closed it. Well, that didn't make any sense. I'm going to take it again. I'm going to type in these numbers: 5, 7, 8, 9, 10, 11, 12, 13, 14. I got 11 in there that time. Okay, I'm going to say save as. I'm going to save it with the name single sample. I have these files somewhere else, and somehow they didn't wind up in. Let's call it single sample t-test, and I'm going to save it on my desktop. Then I'm going to open SPSS. Got to close this in order for SPSS to open it. I'm going to import that file into SPSS. Where'd it go? Okay. Excel files. Okay, files imported into SPSS. First thing I'm going to do is do my descriptive statistics. Descriptives, and I'm going to ask it to tell me the mean and the standard deviation for this sample. Okay, let's see what it gives me. So the mean comes out to be 9.89, and the standard deviation comes out to be 2.934. Okay. Our sample size is 9. You see that there. I'm not going to go back to SPSS. I'm going to tell SPSS I want to do a hypothesis test on this. Okay. My null hypothesis is going to be that the two means are equal. My alternative hypothesis is that the two means are unequal. I know one mean is equal to 8. My sample suggests my other mean is a different value. So I'm going to go in here. I'm going to say, let's see, where are we here? Analyze, compare means. And if you go over to compare means, it says one sample t-test. This is a one sample t-test because we're not comparing two samples. We have one sample and we have a known mean for another population. So we're comparing the results of that sample, the way it represents the second population, to a known population. So I'm going to call it a one sample t-test. I'm going to move the variable into the test variables. And I'm going to tell it that the value that it's going to calculate the mean, the standard deviation, the standard error. I'm going to tell it that I want to compare it to a mean that is known to be 8. See the test value there is 8. Okay. I'm going to click OK. Okay, let's see what our results are here. SPSS does exactly the same test we just did. We assumed a standard deviation 3. SPSS does the same test we just did, except in this case, let's see what it found. Found the mean was 9.89, the standard deviation was 2.93, the standard error was 9.78. Different number because it actually we assumed it was 3. It actually calculated it. What did it do then? It took the value 9.89, subtracted it from the value that we knew 8, right? And it calculated, oh, you want to know something? Degrees of freedom should have been 8, not 20. I was stuck on 25 before. Degrees of freedom were equal to 8. Actually, our critical value of t, I can't get out of this right now. Our critical value of t should have been 2.3, right? Because our sample size was 9. Let's go back here. Okay, so let's take a look at this. So the difference between the value that we are comparing it to, the known mean, was 8 versus 9.89, which is the mean X bar for our sample, is going to be 1.89 divided by the standard error, 0.978. So it's going to be 1.89 divided by 9.78. That turns out to be 1.931. What did I just say that the critical value of t had to be for a sample size of 9, 8 degrees of freedom? 2.3, right? Should I go back there and take a look? The critical value of t for 95% certainty. Oops. Let me get it. The critical value of t for 95% certainty in a sample size of 9, 8 degrees of freedom is 2.3. And how many standard errors apart did we just calculate this to be? Right? How many standard errors apart did we just calculate? 1.931. Are they far enough apart for us to be 95% sure that they're different? Remember, our t-score has the number of standard errors. Our t-score has to exceed the critical value for that sample size. Critical value was 2.3. So it doesn't, right? So we failed to reject our null hypothesis with these numbers. In fact, SPSS, unlike us, who can only go to the t-table to get critical values, SPSS can actually calculate the probability that we would be wrong if we reject the null hypothesis. And what is it predicted to be? Significant. It calls it significance of p-value. Two-tailed, meaning which it says is 9%. Two-tailed because it's 4.5% on one end, 4.5% on the other end. So overall, the probability of us being wrong is 0.09. And what was our acceptable level of error? Was alpha was 5%, right? Our acceptable level of error was 5%. SPSS actually calculates that p-value, the probability we'd be wrong. If we don't use SPSS, we're dependent on using the t-table. And all we can say there is that we have a critical value of 2.3 for that sample size we have to exceed. If our t-score doesn't exceed that value, then we fail to reject the null hypothesis. Okay, I'm going to get you, now you guys can do another one. Let me see if I have another one here. I think there was another one there. Okay, we just did this right here. Okay, let me see if I can't give you some other numbers. Yeah. Here's my folder. Okay, we'll do this one actually comes up twice. The mean number of close friends for a population of people living in New York is 5.7. The standard deviation in this population is known to be 1.3. An investigator predicts the mean number of close friends for introverts will be significantly different from the mean number for the population. Mean number of close friends for a sample of 26 introverts is 6.5. Does this data support the investigator's prediction? Use an alpha level of 0.05. Test the above claim, the 95% count, and a single sample hypothesis test. Okay, so what is our null hypothesis here? Right, we have two means here. The mean number of close friends for normal people, right? And for normal people, and the mean number of friends for introverts. Okay, and our null hypothesis is that the mean number of friends for both groups are equal in both populations. Our alternative hypothesis, right, are not equal. We're not going to make an assumption that one is greater than the other. We're just going to say they're not equal. Okay, so first thing we need to do is calculate a standard error. So the standard deviation for this population is known to be 1.3. I'm going to assume that the standard deviation is the same for both populations. That's 1.3. So calculate the standard error. So let's see. The standard deviation sigma is equal to 1.3. Okay. And so what's our standard error equal to? What's our sample size? Sample size is 26. So what's our standard error? Standard error is going to be equal to, it's going to be equal to 1.3 divided by the square root of 26. Okay, so we're going to calculate the standard error. Once we've calculated the standard error, we're going to calculate either a z test, a z value, or t value. Well, in this case, am I going to calculate a z-score or a t-score? Small sample, right? But what assumption did I make? I assumed that I knew the population standard deviation, didn't I? So the two things that allow me to use the z-test, the z-score, is if you know the standard deviation of the population, right, number one, or if it's a very large sample size. So we've satisfied one of those two. So we're going to calculate the z-value. The z-value is going to be equal to the difference between the mean, which we know for normal people, minus the mean for introvert, x bar for introverts. Right? We don't know that. Over the standard error. Okay. So, and that's going to give us a z-score. Now, in order to say that these two there's less than 5% chance that these two means are the same. What's our critical value of Z going to be? How many standard deviations apart do they have to be 95% sure that they're different? 1.96. So our critical value because we know the standard deviation of the population. So go ahead and do this calculation. Tell me what you get. What is our Z-score? Six 6.5. I'll bring this back up. 5.7, 6.5 are two means. Okay, let's take a look at what we got. I hope you guys gave it a shot, right? Okay, so let's see. The standard error is 1.3 divided by 5. The square root is 26, which is 5.9. Standard error comes out to be 0.22. Right. Oh, I'm sorry. I think you're right. 5.1, I think it should be. Okay, so what does that come out to be? 2 point, what is it? 2.0? Close enough. Okay. No? 0.25? Okay, good. 0.25. 0.25. So, oops, 0.25. So 0.25 is going to be, still going to be I'm going to call it 3.1. So our Z-score, number of standard errors apart these two values are, is 3.1. How far apart do they have to be for us to be 95% sure that we would get that big a difference? Have to be 1.96 because we know, it's either because it's a big sample or we know what sigma is. We know what the population standard deviation is. So since the Z value that we calculated is bigger than Z critical, there's less than 5% chance of being wrong if we reject the null hypothesis. Can we reject the null hypothesis? Yeah, we reject the null hypothesis and we accept the alternative hypothesis that these two means are different from one another. Okay, I can actually go to the Z table and see how likely it is that I would get a value that extreme, 3.1 standard deviations apart. How likely would that be? If I go to the Z table and do that. Okay. I'm going to just take a look at, I'm going to use -3 because it's going to be the same. Again, it's 0.1%, right? 0.1%. Since I always have to be worried about the probability of being wrong on one end, I have to do the same thing on the other end. So it'd really be 0.2%. It would be the probability that we would be wrong if we reject the null hypothesis. Since we have the Z table, we can predict that, right? We can actually look up how extreme, what's the likelihood that we get that extreme a value with Z scores of 3. Now let's do the same thing again, same problem, except this time we don't know. Well, actually, I'm gonna eliminate this part. That mean number for the introverts are different. I'm going to say different still, except this time we don't know what the population standard deviation is. Where is it? Standard deviation of scores in our sample is 1.3, and the sample size is only 26. I can't use Z now, right? I have to use the T values, right? So before we even do anything, let's write our null hypothesis. So our null hypothesis, again, is mu for the normal population is equal to mu for the introvert population, right? And our alternative hypothesis, mu for the normal population, does not equal mu for the introvert population. Okay, that's our null hypothesis. In order to demonstrate this, right, we need to calculate a t-value. How many standard errors apart are these values? Okay, how many standard errors apart are these values? So for a sample size of 26, that what we have here, a sample size of 26, what does t critical have to be for a sample size of 26? Where do we get that? We go to the t table, and it'll tell us how many standard errors apart that these have to be in order for me to be 95% sure that they're different. So how many t-values apart, how many standard errors apart do they have to be? For sample size of 26, 25 degrees of freedom, they have to be 2.06 standard errors. So my critical value, right, my t critical is equal to 2.0, what was it again, 2.06? 2.060. Okay, so now we have to figure out whether they're really far enough apart, right? Whether we exceed that critical value of t. Okay, so calculate our standard error. Our standard error is equal to, what's it equal to again? It's equal to, where is it? 1.3 divided by the square root of 26. And what did that come out to be again? You guys remember? 0.25. Okay, and we're doing exactly the same calculation, right? Our t-value now is equal to 0.8, which is 6.5 minus 5.7 is 0.8, divided by our 0.25 is equal to 4. Our t-value is equal to 4. I don't think we had the same numbers before, exactly. It came out to be 3.7. It wasn't 0.25, it was something else, I think. Okay, so our t value comes out to be 4. Have we exceeded the critical value of t? Yes, right? Our t-score, there are 4 standard errors apart. Our t-score has exceeded the critical value of t, so we can, what can we say about our null hypothesis? Can we reject it? Right? T is greater than t critical, So if t is great, if t is greater, our t value is greater than t critical. That's the same thing as saying that the probability of being wrong is less than 0.05. Okay. Let's say a t-score, let's see. Okay, let me see if I can't come up with another. Let me give you a different example. So we got a single sample t-test in this. That was this one. Which really means that. Okay, let's look at this one. Mean SAT score for the population of first-year students at Hunter is 620. The standard deviation of scores in this population is 95. An investigator believes that the mean SAT score for the first-year psychology majors is significantly different than the mean score for the entire population, for the rest of the population. The mean of a sample of 25 randomly selected first-year psychology majors is let's say we don't know what it is yet. Without knowing what it is, let's state a null and alternative hypothesis if we want to test whether or not psychology majors have a different mean SAT score than the rest of the Hunter population. So what is our null hypothesis going to be? The mean SAT score for, it's not hard, somebody yell it out. The mean SAT score for all students, right, is equal to the mean SAT score for psych students, right? I think they're all first-year students, right? Let's see, let me go back there and take a look. Mean SAT score for the population of all first-year students versus first-year psychology majors, okay? Psych majors. U for all, U for psych majors. Okay, what's our alternative hypothesis? U for all students is what? Is not equal, right? U for psych students. Okay, so how are we going to prove this? We're going to prove this, first of all, number one, what do we know? We know that the mean for all students is equal to 620. Do we know the mean for psych students? The mean for the population of psych students? Do we know what that is? No, we don't, right? We only know what X bar is, right? We only know what the mean for our sample is for psych students, right? What's that equal to? That's 648. Okay, so now we want to demonstrate that we can say that the mean for the population of all students is different than the mean for the population of psych students, even though we only know what the mean is for the psych students, what the mean of our sample is. What was the size of that sample? Size of that sample was equal to, let's say, what was it again? Was it 25? 25. 25 randomly selected students. That means equal to 25. So I'm going to say that, so we need a standard deviation here, right? So we can calculate our standard error. Do we have a standard deviation? The standard deviation of the population is 95. Okay. So for the moment, I'm going to say that we know sigma for the sigma for the psych students. Right? That's it. We're going to assume that it's the same. We know sigma. Right? So What's that? That's for all the students, but I'm assuming that it's true for the psych students also. If I make that assumption that I know what sigma is for the psych students, now I can calculate a z-score. Right? Right, okay, so let's do this. Let's calculate the standard error. The standard error is equal to, it's going to be equal to the difference between the two means, right, which is 620 minus 648, divided by the standard error. Well, first I got to calculate standard error. What's the standard error equal to? It's equal to sigma over the square root of the sample size. Square root of 25 in this case. That's equal to 95 divided by 5. And that's equal to, what is that, 19, I guess, right? Equal to 19. So I'm going to take this and divide it by 19. So, what is this value? The difference between the two means divided by the standard error. What is that value? Is that z or t? I know sigma, right? So what is that? That's z, right? Okay, so z is equal to that value. So what is that value? Equals, right? What is that? That's 28 over 19. That's 28 over 19. 1 point, what? Okay, 1.47. So if I'm doing this, what is the value of z I have to exceed, critical value of z, that represents 95% certainty or less than 5% chance of being wrong? If I say that these two means are different, what is that z critical? What is it for 95%? 1.96. What would it be if my alpha instead of being, right, that's true, this is true, that's my critical value, for alpha equals what value? 0.05. What if I told you that alpha is equal to 0.1? What would z critical be then? Wrong direction, right? We want less chance of being wrong. Okay, so what's it going to be? Right, we have to have them further apart in order to reject the null hypothesis. If we want a higher level of certainty, 2.58, right? But we're satisfied with 1.96, and alpha is equal to 0.05. Okay, so what is my z value again? My z value is equal to 1.47. Can I reject my null hypothesis? How far apart do they have to be? How far apart are they actually? 1.47. So the two means are not far enough apart for me to say that they're different, right? So what do I do with my null hypothesis? Bingo, that's it. That's as hard as this gets, especially with a single sample t-test. Now, let me do this again, except this time I'm going to do the same thing, except this time we got that 95, let's see. This time, well, before we do that, I'm going to change something here. I'm going to say that the psych students are, let's see, let's make them really smart. Okay, let's make this 698. Okay, 698, the difference between the two of these is how much? 78. 78 divide, oops, I'm sorry, that's 25, that's these. What was that again? That was 19. Okay, so that's 78 divided by 19. Is equal to 4.1. Big difference, right? So this is actually, they're not that smart. Make this a little bit smaller. I want to make this, you know what I'm going to do? Let's see, 38. Okay, I know what I'm going to do. I'm going to make this 58. Okay, 58. Okay, what does that come out to now? That's 620 minus 50 is 38 over 19. It's equal to 2.0. 2.00. Okay. Okay, and we know sigma. I'm assuming we still know that the population standard deviation 95, and our z-score comes out to be 2.0. Z critical, since we know what sigma is, or it's a big sample, Z critical is 1.96. Do I reject my null hypothesis? Yes, I do, right? Because it's 2.0, I only need 1.96. Okay, so now let's assume that that 95 was not sigma, but it was the standard deviation of my sample, and it's a small sample. So now I can't use Z for my critical value. I have to use T critical, right? And I have to use T critical for how many degrees of freedom? Right, that was sample of 25, so degrees of freedom equals 24. Right? So what is T critical? What is T critical now? T critical now, instead of being 1.96, is, you remember it, right? Okay, equals, where's T critical and where am I here? Okay, equals 2.064. Okay, for alpha is 0.05, right? So let's see, 620 minus 658 over 19, my T score is, right, still 19, my standard error is still 19, 95 over 5, over 5, because sample size is 5, right? But this time my T value, since I only know the sample standard deviation, the sample size is only 25, I have to use the T value for my critical value, which is equal to 2.064. But I calculate my T score is 620 minus 658. They're 38 apart, and the standard error is 19. They're exactly 2 standard errors apart. Is that enough for me to reject the null hypothesis now? No, it's not. So the same numbers, right? In one case, we rejected the null hypothesis. In the other case, we didn't reject the null hypothesis. Why didn't we reject it? Because in the second case, I needed for them to be further apart because I was using the T value instead of the Z value. Okay, I needed more certain. I was less certain of the standard deviation of the population. Right. So in that case, we failed to reject the null hypothesis.